Okay, so for our types of reactions lab, it's always best to get to do the lab yourself, but to try and recreate that here, I'll do the reactions, but you should pause this, read the instructions, so you know what's happening in that. Watch the part A and then do that, and then back and forth kind of thing. So I just grabbed a test tube. And not only is it kind of dirty, but it's also got a crack in it. So you always want to look at test tubes, especially if you're going to be heating them before you start. So for reaction one, I've got a new test tube, by the way. For reaction one, we're supposed to get about 1 gram of sodium bicarbonate, commonly called baking soda. When amounts matter, we want to make sure and measure measure precisely and stuff, but this is qualitative, right? So we're looking to see what happens, not exactly how much of things. So a small scoop is about 1 gram, right? To make it easier for y'all to see, I'm going to do a little bit bigger than normal. Whenever I heat a test tube, I want to make sure and use test tube tongs. And then I'm going to set it up so it's pointed towards the outside wall like this. So I am not endangering myself or people around me and that kind of thing. We're going to do a burning splint test. To do a burning splint test, 3 things can happen, right? It could make the flame grow brighter. If I'm generating oxygen gas, it's, oxygen helps things burn, right? It's one of our reactants in combustion, so it would burn brighter. If it puts the fire out, then I've generated some sort of gas that is not flammable, or the gas itself could burn. So we'll see what happens there. This reaction is pretty quick. So we've got to have our splint burning before we start. So we'll start our splint burning. And then let's make sure y'all can see okay. So watch the test tube and then the splint itself. This reaction doesn't take real long. So you see how the fire burns okay out here. It is definitely putting that fire out as we go to the mouth of the test tube. So definitely indicating that we are generating some sort of gas that is not flammable. If we look at the sides of the test tube, we can write some observations down. Looks like there's some water droplets along the side. Some of the powder's been moved up along the side. The reaction's probably pretty close to done. You can see, I can see a little bit of smoke coming out of the top of the test tube. But if you look at the reactants and products, right, there is no longer baking soda in the test tube. There's not sodium bicarbonate. Look at the reactant. Look at the products to figure out what is in the test tube now, right? So what is in the test tube is another solid. So if you look at the phases on those things, right, you should be able to figure out what the solid is. I can see some little droplets of something along the sides of the test tube there, right? Some little droplets of some sort of liquid. Again, look at the products to figure out what that is. And then the gas that we generated put a fire out. So read that section and that should make sense of that. Also, on that same note, the powder that we put in here is different now than the powder that was there before. So go ahead and pause the video and take a few minutes to figure out what's going on in reaction A. Now, things that you're not sure about, if you're during class right now, go ahead and jump back into the WebEx or something and talk to me about it. If it's, outside of class time, shoot me a message in Teams or something and we can talk about it. But we should understand, we're trying to bridge the gap of what's happening on paper with what's happening in the test tubes. So for part B, we're going to react a sample of elemental iron, right? Fancy elemental iron can be bought at Lowe's in just nails, right? So elemental iron and copper 1 nitrate, and the lab says to get 15 milliliters. So when we measure, right, the volumes on here are just for estimating. Graduated cylinders are much more precise. There's no such thing as exactly 15 milliliters, right? It's just how precise you want to be. So I want to get eye level with it, read the bottom of the meniscus kind of thing. I'll be holding it, but you can kind of see there that is 15 milliliters. Now, again, this is more qualitative than quantitative. So the exact amount here isn't critical, but we're trying to learn how to measure and go back and forth and that kind of thing. So we don't ever want to pour it back into our original container because that can contaminate for everybody because, hopefully this is clean. I rinsed it out and that kind of stuff, but you never know. So we make observations about each one of them beforehand, right? And you can, so make some observations about those beforehand and we put them together. And then we're going to have 10 minutes on YouTube of you staring at this. no, that would be kind of a waste of time, right? But we will look at it, and then we'll come back and look at it here in a little while, right? So I'm going to pause the video. We're going to set up part C while we're waiting for part B to react, and then we'll come back, right? So there's no reason to waste time sitting here waiting for something to react. So here it is. It hasn't really changed to my eye much yet, but what we're expecting to see some changes there in a minute. So for part C, we've got a couple beakers. It tells us to get a scoop of copper 2 sulfate. Copper compounds tend to be blue. You notice the copper nitrate was blue. This copper sulfate is blue. So it works out, right? So this is our copper sulfate. And then it says to get where did my calcium go? And it says to get a scoop of calcium chloride. That's the same chemical we used in the chemistry in a bag lab. That was like the forbidden Dippin' Dots stuff. You can see it's like little round BB type things. And then we're going to dissolve each of those in 20 milliliters of water. So for something like this, you definitely want to use distilled water. So distilled water, we get out of the still, right? So it boils the water, recatches it as just water, so it leaves the minerals behind. We don't want side reactions and stuff like that. So we'll get 20 milliliters. I think it's 20, might be 25. I'll double check. But we want 20 milliliters of each of these. So 20 milliliters in our calcium chloride, and 20 milliliters in our copper sulfate. So just poured those in, right? Nothing fancy there. So they started off as solids, but solids don't react very well. So we're dissolving those in water, so they'll be aqueous. So we can see that water starting to turn blue now, and the copper sulfate is dissolving. Right, so these little guys, and just like in the chemistry in a bag lab, this is starting to get a little bit warm. That's sometimes, reactions can be endothermic, sometimes they can be exothermic. Just kind of depends on the reaction. And we'll give those a minute to dissolve. Again, read parts B and C. This video's, I'm condensing all the work down, but there's a lot to do in between. So we should be pausing this and reading through that and that kind of stuff so we can make sense out of what's going on. So check back in with both of our reactions. Our reaction B, remember, was elemental iron and copper nitrate. That is starting to get a little bit of like a brown substance on it. I don't know how well you can see that color there. Maybe I'll take it out for a second. So you see how it's starting to get a little bit of a brown substance on it. In real lifetime, that's been about 2 minutes, maybe 3 minutes. And our copper sulfate is dissolving, and our calcium chloride is pretty much dissolved, right? So still got a little bit there, but it's pretty much dissolved. We're going to give those time to react. Now, some reactions happen like instantly, right? Like that sodium bicarbonate, the baking soda, when we heated that reaction was like, the whole thing was like 15 seconds. These need some time to dissolve, and then they'll need some time to react too. Some reactions take a little bit more time. So for reaction C, these are all the way dissolved now. I don't know how well you can tell online, but the blue's a little bit darker now. The more of it dissolves, the darker it gets, right? And our calcium chloride's all the way dissolved. So if I pour those two together, right? It doesn't really matter which one I dump into the other one. When I initially pour them together, I'm not seeing a whole lot. We want to stir them and give them a second. Again, this is one that takes a little while to react. So we're going to give that some time. We're going to set that aside, and then we're going to filter it after it's had a chance to react. My iron nail is still reacting away. Just takes a little bit of time. I've got one that went yesterday that we'll look at here in a minute. But while we're waiting for those, we'll go ahead and do part D. For part D, it says to get some steel wool. Steel wool is made out of iron also, just like a nail. So my reactant, at least one of my reactants, is iron. We want a fairly small piece. We don't need a whole ton. We'll look at it. Let's see. We have enough light on that. So it's nice and kind of shiny gray, as you would expect it to be. If I pat it and stuff, it doesn't fall apart into 1,000 pieces, right? Because metals are malleable. I've got test tube tongs right here, but test tube tongs are not for putting into a fire. We're going to put this into a fire, and so we need to use crucible tongs for that. So crucible tongs are across the room. So if you look at our reactants, they're iron and oxygen is just out in the room, so I don't have to do anything fancy to get that oxygen. I wonder if this would be easier to see in the dark. Probably not. So we'll just turn our heat source on, move stuff away. Right, anytime I'm going to heat something, I want to move things away from it. I'm going to hold it here. Whoa. So it started to react there. Just kind of moving it around in the fire, giving it all a chance to get hot. Definitely has a smell to it. The in-person kids have been complaining that it smells. To me, it just smells like chemistry. So when you look at it, you might say, well, that's like the same color that it was before. It doesn't really look any different now, but I'm going to let it cool off for a second. This is pretty warm. Still pretty warm. And if I open it up, can you see that stripe on there? So where I was holding it, it's still like real gray, right? And on the outsides, it's kind of a bluish color. So where I was holding it, no oxygen could get to it. So it didn't get a chance to react there. It got hot there, but it didn't get a chance to react because the oxygen couldn't get to it. So kind of like with the Torch Magnesium Lab, when we put the crucible lid on top of it, no oxygen could get to it, so that stopped the reaction, right? So we can make some observations there. Something else to point out. Let's see, I need some white paper for this so y'all can see it okay. Something else to point out now, right, for our observations. If we tap it on the paper, look at how brittle it's become. Can you see? Yeah, you can see those little crumblies on there, right? It's gotten real brittle. So before, it was real malleable, and now it's brittle. Well, metals are supposed to be malleable, not brittle. So this isn't a metal anymore. Now, we didn't make it a non-metal, right? But look at your products. That's not a metal. That's a compound, right? So we should be able to figure out what this blue, I call it blue stuff, right? We should be able to figure out what this blue stuff is on that. So that's part D. And again, the goal is kind of figuring out what type of reaction it is and that kind of thing. Feel free to jump into the WebEx and we can chat about the different ones. There we go. This guy's started to really turn now. So we can really see the color changes. All right, now one of the questions says, what's the stuff on the nail? It's definitely not rust. Rust is not one of our products. So when on the labs, when I'm asking like what these different things are, we don't want to just guess at any random chemical in the whole world, right? Look at the reactants and look at the products. It's got to be one of those things that are there. This is one that's been sitting overnight, right? So there is a reddish solid at the bottom and the solution is now orange, right? So the solution is also not rust, right? It's an iron compound, right? But look at your products. You can figure out what in the solution could be giving us an orange color. But there's a red solid at the bottom, right? Again, looking at the products, you can figure out what would the solid thing be? What would that be? And there's a yellow-orange solution. So this is after just a few minutes. Now this was a smaller one. This was a shorter one, so it like laid all the way down in there. But I let that one react overnight, and that's what it looks like. Here's our part C. It has started to get a little cloudy, but it's not quite ready to filter yet. This one takes a few minutes. So we're going to give that a couple more minutes, and then we're going to filter that. Doing some cleanup while I'm waiting for those things. Most things are safe to go down the drain. We want to be careful with stuff, right? We don't put anything hot down the drain. And we don't put, in general, we don't put colored things down the drain. There are a few most of your transition metal compounds are colored, but there are a few that are safe to go down the drain, but it's just a nice safe bet that if it's colored, it's probably not going down the drain. Like copper can kill bacteria. And wastewater uses bacteria to clean the water. So I don't want to send copper compounds down the drain. Now, a drop or two, a flake, whatever here or there is not going to cause a big problem for wastewater. But if we go send in pounds and pounds of copper down the drain, that definitely causes a problem with wastewater. So we would never want to cause a problem somewhere. So copper compounds will react and neutralize them, right? Turn them back into a solid, basically, and then I can throw them in the trash safely. Or you can hang on to them and dispose of them with a heavy metal waste if you've got other things like lead and cobalt and that kind of stuff that you don't want to send down the drain. Solid things in general are pretty safe to put in the trash, but we want to clean out our test tubes and that kind of stuff as part of our lab. So our solution has gotten pretty cloudy. And so we're going to filter it. One of the nice things about filtering is then we can see what our precipitate, the solid, what color is that, and try and figure out what it is, and what color the filtrate, the solution that goes through the filter paper is. So when we want to use a filter paper, we take a filter paper, we fold it in half. We fold it in half again. Right? So I like to think about things in terms of food, right? So we go from pizza to taco, and then from taco to bird, which, I mean, you can eat birds. You don't normally eat birds when they're like this, right? But we eat chicken and stuff. So then what students will usually make the mistake of doing that is they like try and roll this and like stuff it down in the funnel. Well, if I roll it, right, there's a big hole that stuff can go through. So I don't want to roll it. There are 4 slips of paper now, right? 1, 2, 3, 4. I want to open it so that there's 3 on one side and 1 on the other. That way the solution has to go through my filter paper. And then I use the funnel to hold it up. And then we just kind of give it one last swirl and pour it in. Now, the reaction might not be completely done. So we might see it as it filters through. It might continue to react after it goes through. If we really wanted to, if we cared about something more than just what colors or where, we'd probably want to, heat this for a little while to make sure it was, and then let it cool back off and that kind of thing. So we're gonna, you can see it dripping through there. I'm gonna pause it so you don't have to watch it filter the entire time because you just fast forward through that anyway. And then we'll come back and figure out what colors are where. So if we look, we can see that the solution coming through here is blue, right? It's clear. I can see through it, and it's definitely blue. Well, we can use color to help us follow and figure out which chemicals are where, right? Copper compounds tend to be colored, right? We saw copper sulfate was colored, copper nitrate was colored. So it's pretty safe to assume that the copper compound that's our product here would also be blue in color. So when we're figuring out phases here, we can look at find the copper and say, oh, well, the copper is stayed in solution and is the filtrate now, right? So filtrate's the liquidy part. And so then the solid that's going to get caught in the filter paper, we can figure out what color that is here in a minute when it's done filtering. Okay, we should really take more time than this, but the bell is going to ring soon, and so we don't have a ton of time, right? So we can see the blue filtrate there. There is still blue in here because there's still stuff filtering through, but you can start to see some solid white on the side. Now, there's not a ton there because it's mostly down on the bottom. I don't know if you can kind of see the darker color at the bottom. It almost looks a little green. Well, there's still copper filtering through there, not copper, and not elemental copper, right? But copper ions that are doing that. So again, do what you can on the lab, and if there's things that are not making sense, things that I went too fast on or whatever, you got to communicate with me on that. But we're trying to figure out how to figure out what types they are. So compare the reactants and products and stuff to our types of labs or our types of reactions and that kind of stuff, and then talk to me about things that we're not sure about. Have a good one.